Welcome students. Today we will start off by doing this question, Laplace transform of f of a(t). Now by definition we know that Laplace transform of f of t is equal to integral 0 to infinity e raised to the power of negative st f of t times dt, and we write that to be equal to f of s. In other words, you can also state that f of s is equal to integral 0 to infinity e raised to the power negative st times f of t times dt. Now with this definition we will be working out with this. So let us just consider Laplace transform of f of a(t). Now in place of t we have got a(t), so this is equal to integral 0 to infinity. In place of the function we will just have to use a(t), because in place of t we have got a(t). So this is going to be e raised to the power negative st times the function is a(t) times dt. And don't write anything for f of s. Let us just focus on this particular transform. Now what I wish to do is I would have to change this a(t) to represent a single function. And more so, another important fact you got to know here is the value of a is greater than 0. It's not negative. Now what I would do is I would just take, let some p be equal to a(t), and I differentiate this. So dp will be equal to a times dt, and from here I can write dt to be equal to dp over a. Okay, so this is going to be equal to, I'm not going to change the integration limits for now. Let me just make the substitutions. Now this is e raised to the power negative s. In place of t, from here t is equal to p over a. Right, so substitute p over a times f of, in place of at I've got p, in place of dt I've got dp over a. Now what happens to the limits? Let us handle the limits here. When t is equal to 0, the limits of p will be equal to 0. When t is equal to infinity, p will be equal to infinity. So this is going to be 0 to infinity. Now a is a constant, so you take that out, so it's going to be 1 over a. Integration is from 0 to infinity e raised to the power of negative s p over a f of p times dp. So this is what we have got. Now clearly if you were to compare here with the original definition, I've got a p here instead of t, I've got a p here instead of t, but the only situation that I've got here is I've got a negative s times p over a. I got to have a t. In other words, I got to have a p alone here. So what I'm going to do is I'm going to rewrite this as 1 over a integral 0 to infinity e raised to the power. Instead of a occurring below p, I would like to write this as negative s over a times p times f of p times dp. So this is the way I would like to write. Now if you were to see this, in place of s I've got s over a. Okay, so let me write this like this: 1 over a integral 0 to infinity e raised to the power negative of s over a times p times f of p times dp. So now you can see that in place of s I've got s over a. Of course the negative sign is occurring in both the terms, and I've got a constant 1 over a. Now this is just going to be following us, but if you were to see the integration, this is similar to the integration definition that we add for Laplace transform of the function f of t. So I can clearly write, in place of f of s, I should say in place of s I can substitute s over a. So that would mean I now have f of s over a. I hope you are following this. When I have s, I got the function to be as s. When I have s over a, I need to have the function as s over a, f of s over a. So therefore, to sum up Laplace transform of f of at is equal to 1 over a f of s over a. So students, we are going to find out how exactly we could use this result. Students, we will be using this definition to solve a few questions. So foremost, let us find out the Laplace transform of shin at. Now, we already know that the Laplace transform of shin t is equal to 1 over s squared negative 1. Now, by using this definition, Laplace transform of shin at can be rewritten as 1 over a f of s divided by a. So that would mean, in place of, say this, let me rewrite this to be as f of s being equal to 1 over s squared negative 1. So in place of s, all I need to do is substitute s over a. So this would mean I get 1 over a, 1 over s over a raised to the power 2 negative 1. Now I can rewrite this as 1 over a of 1 divided by s squared over a squared negative 1, which can be rewritten as 1 over a of 1 over, I'm taking a squared as the LCM, so it's going to be a squared negative a squared divided by a squared. If I were to flip this, I would get 1 over a. This is going to be a squared over a squared negative a squared. So clearly a and a can be cancelled, giving me a over a squared negative a squared. This is my Laplace transform of shin at. Now, if someone were to ask us, how are we to show that this is true? So, it can be easily shown. So, let us just consider, I'm going to show you that Laplace transform of shin at is truly a over s squared negative a squared. Now, we know that shin t can be rewritten as, in fact, shin theta, or let me use shin theta. Shin theta can be written as e raised to the power of theta, negative e raised to the power negative theta divided by 2. Okay, this is the expansion for shin theta. So shin at can be rewritten as e raised to the power of, in place of theta, substitute at. So it's going to be at negative e raised to the power of 80 divided by 2. Now this can be rewritten as, I want to take 1 over 2 out. In fact, this can be Laplace transform of e raised to the power of 80 negative e raised to the power of negative 80, which can be rewritten as 1 over 2 Laplace transform of e raised to the power of 80 negative Laplace transform of e raised to the power negative 80. Now this is equal to 1 over 2 times. Now Laplace transform of e raised to the power 80. What is that? That is nothing but 1 over s negative a. Negative. What is the Laplace transform of e raised to the power negative 80? That is going to be 1 over s positive a. Now if I were to take the LCM, s negative a times s positive a, I would have s positive a negative of s negative a. So that is going to be equal to 1 over 2 times s positive a. Let me rewrite it like this: positive a negative of s positive a divided by s squared negative a squared. Now positive s negative s gets cancelled, so s add a added with a would give me 2a divided by s squared negative a squared. So 2 can be cancelled, giving me a over s squared negative a squared. So what is this? This is Laplace transform of shin at. So this is exactly what we have got using the formula. Okay, one more illustration in terms of cosines. So imagine you are asked to find Laplace transform of cos at. I'm going to use this definition. Laplace transform of f of at is equal to 1 over a f of s over a. And by this definition, I'm going to apply this definition to Laplace transform of cos t, which is equal to s divided by s squared positive 1. So therefore Laplace transform of cos at is equal to 1 over a f of s over a. This is actually f of s, right? So this can be rewritten as 1 over a. In place of s, I need to substitute s over a. So it's going to be s over a divided by s over a raised to the power 2 positive 1. So I can rewrite this as 1 over a of s over a divided by s squared divided by a squared positive 1 is equal to 1 over a s over a. LCM is a squared, so it's going to be s squared positive a squared divided by a squared. I can rewrite this as 1 over a. Now I can place a s, move the a to the denominator. In fact, let me just have it like this, and then I will use this step to rewrite this as s squared positive a squared. If I were to flip it, this will be going up to the numerator. So this 1, I'm going to rewrite it as a squared. So this is going to be equal to a can be cancelled, giving me a. Now s slash a, this can be rewritten as s with a being pushed to the denominator, and then you got s squared positive a squared. So a can be cancelled, giving me s over s squared positive a squared. So this is nothing but the Laplace transform of cos at.